Hi, everyone. Thank you for joining us today for this wonderful event. Thank you to COSPAR and all of the partners for asking Goddard Space Flight Center to be a part of this amazing virtual event that you guys have going on today. My name is Brianna Horton, and I am one of the 10,000 employees that work for NASA's Goddard Space Flight Center. Goddard Space Flight Center is one of NASA's 10 centers and the best, but I'm not biased. So I want to make sure that everybody gets to fully engage with this amazing panel that we have today. So the chat feature has been enabled, so please make sure to drop your comments and questions for our amazing panelists throughout the entire 1 hour that we have to spend with you. We will get to your questions at the end, but without further ado, I would like to cue up the video about NASA Goddard Space Flight Center.
At NASA Goddard, we build space telescopes
to explore the evolution of galaxies, stars, and planets that make up our universe.
We discover planets around other stars and investigate whether they could support life and what that life might look like.
We imagine, then engineer far-out missions to answer questions about how galaxies and planets formed and evolved over time.
At NASA Goddard, we study the sun's dynamic behavior and the space weather that it generates so we can protect astronauts and satellites in space as well as our technology on the ground.
At NASA Goddard, we use the data from a constellation of satellites to generate global maps of rain and snow pummeling the Earth.
To monitor how greenhouse gases move through the atmosphere.
And to model all of the Earth systems to create a dynamic portrait of our planet.
We launch small rockets carrying university-developed experiments into space.
And provide low-cost space platforms for testing new instrument concepts and engineering techniques.
At NASA Goddard, we ensure every craft is space-ready.
We blast noise and shake instruments to simulate stresses at launch.
We expose them to the unforgiving vacuum of space and to the powerful magnetic fields.
At NASA Goddard, we develop and maintain communication links between Earth and spacecrafts in orbit.
We evaluate and improve system software to reduce risk in our missions, large and small.
Innovation and science never sleep.
And new discoveries never get old.
At NASA Goddard.
Good morning. Welcome to the What is Goddard panel. I'd like to welcome you on behalf of the Director of NASA Goddard Space Flight Center, Dennis Andrusek. I'm Dr. Joe Hill-Kittle, and I'm the Deputy Director for the Sciences and Exploration Directorate at NASA's Goddard Space Flight Center. Before we get started with the panel, I just want to take a couple of minutes to give you a bit of background on Goddard. Goddard was established in 1959 as NASA's first spaceflight center. As Bree mentioned, Goddard has about 10,000 people and is one of 10 major NASA field centers. And it's called Goddard in recognition of American rocket propulsion pioneer Robert H. Goddard. As you just saw in the movie, engineers, project managers, and scientists at Goddard work on the entire life cycle of a mission. It starts with the development of the initial science questions that lead to a mission idea, and then the design through the building of the mission, launch, and then there's the on-orbit operations, the gathering and analyzing of the data to then answer the science questions, which then leads to new questions and new missions. Goddard's Sciences and Exploration Directorate is the largest Earth and space science research organization in the world. And so here we have to talk with you about some of the amazing science, technology, and missions is our panel. I'd like to introduce to you Mr. Brian Roberts, Deputy Director of NASA's Exploration and In-Space Services, Nexus, who will be describing some of the satellite servicing technologies. Dr. Dalia Kirschbaum, our Chief of Hydrological Sciences Laboratory in our Earth Science Division, who will share how we strive to understand our changing planet. Dr. Antti Pulkkinen, our Acting Director of Heliophysics Science Division, who will describe the exciting missions and science in his division. Mr. Michael Amato, the Manager and Lead Engineer for our Goddard's Planetary and Lunar line of business, and is responsible for identifying the next generation of missions. Dr. Knicole Cologne, an astrophysicist who works on the Transiting Exoplanet Survey Satellite, and also the Deputy Project Scientist for the Exoplanet Science for the James Webb Space Telescope, and who'll discuss our search for planets outside our solar system. And finally, we have Miss Bree Horton, who will be our moderator for today and will be helping ask the questions of the panel. And so, Brian, it's over to you.
Great, thank you. Well, hello, everyone. Honored to be here. I did visit your country back on my honeymoon many years ago, and it was a beautiful country, so I'm looking forward to being back at some point on vacation. As I said, I'm going to talk a little bit about some of the satellite service technologies we're developing at Goddard to make satellites last longer, to collect more science data, and enable exploration of humans into the universe. Next slide, please. So a little bit about me. I grew up in Northeast Ohio, which is kind of near the Great Lakes, kind of in the northern part of the country. I have a Bachelor's of Science degree in Aerospace Engineering that I got from Cleveland. And during my time as a student, I actually interned as a student intern at little less than half of the NASA centers that Bree mentioned in her introduction. I then came to Maryland, which is kind of right outside Washington, D.C. I got a master's degree in the same field. And this was when I really first started getting involved with space robotics. The other unique thing, too, is I actually got funded by NASA to go to grad school, which means I didn't have to take out a bunch of student loans. So I'd advise any of the students out there looking to do similar work, look for opportunities like that to get funding to do the work that you're passionate about. I've been working at Goddard for a little over 12 years or so. I first started off as an intern, and then I went off to grad school, and I came back and worked as a contractor for 8 years. Of the 10,000 employees that Bree mentioned, about a third of those actually work for the federal government. And about 2/3 of those are contractors that get hired by various companies around the Washington, D.C. area. So I worked as a contractor, and more recently, for about 5 years, I've been a civil servant at Goddard. Next slide, please. So some of the technology you develop, if any of the students out there or anyone out there has been working in robotics or putting mechanisms and things together, there's a couple of various things that you need to be able to do that. You need computers to communicate and send programs to the mechanisms you're trying to do something. And same thing for robotics, is we have a central computer that has all the commands that makes the robot do what it needs to do. And you can see those are some of the technologies here that we develop. We also have, obviously, robots that go up and fix satellites, put fuel in satellites, change out instruments like we did on the Hubble Space Telescope with humans. We were able to send the shuttle up and change out instruments and various parts of the telescope, the batteries and things like that. We're now looking at doing that with the robotics, so we need to develop those robot arms. Unfortunately, most satellites are not designed to be serviced, so the other thing we need rendezvous sensors to actually be able to find the satellite, to be able from far away to determine that the satellite's in a certain direction, to know how it's moving so we can kind of catch up to it, get close by it so that the robot arms can reach out and grapple it, and then go to work and service it and fix it. So those are some of the technologies on the left. Once we've grappled the satellite, we have things like fluid transfer systems, putting gasoline or types of propellant in the satellite, just like you put gasoline in your cars. We have those sorts of technologies as well to make that happen. And then finally, on the right is kind of the missions that are enabled. There are missions that will be enabled by putting fuel in the satellite to keep a satellite going longer. Right now, the kind of the paradigm in space flight is once a satellite runs out of fuel, we essentially throw it away and launch a new satellite in its place. So by putting fuel in a satellite, can keep it going longer and return more science. We can also build large structures. Right now, we're limited on how big we can fit things inside a rocket, and rockets aren't normally large. They have a certain size. So if you want really large telescopes to gather a lot of light from far off galaxies and stars in the universe, we need to build things in space. And so by having robots in space to do that, you can enable more science to be collected. So those are some of the missions that are enabled by having these technologies developing at Goddard, being used in space. Next slide, please. So in this slide's a video of some of the work we've been doing. The top left video is some work we did on the International Space Station. There are many robots up on the space station provided by various countries. And what we did at Goddard is we built tools that you can see in the top video there that can work on satellites. And we wanted to demonstrate that robots could do these sorts of tasks on a real satellite. So what you see in the video here on the top left is a valve that you would put fuel in the satellite. So it allows us to practice in the lighting conditions and the zero-G you have in space. The bottom video shows the same sort of thing. We're doing various tasks on the space station. Finally, in the bottom right is the ultimate mission we're going after, is going up and refueling a satellite in space, which has never been done before by a robot. Again, most of these satellites are launched without any plans to put fuel in them in the future. So if we can keep satellites going longer, we can return more science to the scientists and keep these things going much beyond when they were designed to. And then finally, the top right video shows us doing a real live satellite demonstration, refueling down at the Kennedy Space Center in Florida that we could not do in space. So it's really using the real propellant you would put in a satellite and showing how we can do that remotely, actually controlling the robot from Goddard in Maryland with a couple-second time delay, which is what you would see in space. So it's just some of the ways we practice on the ground and in space, so that when we go and do it for real, we've been practiced. Just like in school, if you take a quiz and an exam and your final exam, you don't just jump to the final. Or if you play sports, you don't just go and play in the championship game. You have practices, and then you have expedition games, and you have games you play, and then finally the playoffs. And same thing here. We practice before we go do the real thing in space, which is in the bottom picture there. Next slide, please. So just show some of the other missions that are enabled as we start looking at sending humans farther out into the universe. By having refueling capabilities allows those spacecraft to go further, to launch maybe with not as much fuel in them, which means we can launch more food and supplies for the astronauts. We can also service things on the moon by setting up habitats on the surface and building really large structures, big intergalactic spaceships to be able to go off into far reaches of the universe and send humans out there by using robots to put those together and service them. Are all important things we want to do as a spacefaring nation going forward. Next slide. I think that's the last slide. So now I'll turn it off to Dr. Kirschbaum to talk about the work she's doing.
Well, thank you so much. So I'm excited to talk about how we are using all of the different tools at NASA to understand our changing planet. So if you go to the first slide, first, a little bit about me. I started really early liking math, but I didn't quite know how to apply it. And so through lots of courses in math and geoscience, I found a love of natural disasters. And so what do you do with that? Well, I got a PhD, and I found that we can use all of these different assets, all these different satellites we have in space to better understand disasters and hazards on Earth. And so I was fortunate enough to get a postdoc after I finished my PhD at Goddard Space Flight Center. And so the image on the right is one of my most favorite experiences thus far in being at Goddard, which is I got to stand in front of a fully assembled satellite that was about to be launched to measure rainfall around the world and really save lives, save property, and help us understand our changing planet. So if you go to the next slide. Well, why are we talking about Earth science, right? I thought NASA's all about robotics and space. And absolutely that's the case, but we actually have over 24 satellites with their eyes pointed down at Earth, trying to understand and take the pulse of our home planet. We ask questions like, how is our Earth system changing? What causes these changes? What will happen in the future? And how does that affect other people and society around us? But with all of these different satellites and different orbits around our Earth, we can't just look at each process individually. So if you go to the next slide, we really need to look at these as a system of systems, really, right? How does the changes in sea surface temperatures affect the weather that we have? How does the green or the vegetation we have on land influence what goes into our water bodies and how wet the soil is? And then what's the relationship between rainfall and all of these different processes? And how can we model them to understand not just one process, but all of it together? So if you go to the next slide, one of the missions that I have been working on, and that's the satellite that you saw before, is the Global Precipitation Measurement Mission. And so what's exciting about this, it was launched in 2014 through an international partnership with NASA and Japan. And so together, working with the Japanese as well as different space agencies from around the world, we are able to take a group of different satellites to look and get a global picture of how rain and snow is changing around the world. And so if you go to the next slide, what this allows us to do is it allows us to see where storm systems are originating in the southern oceans and how they move all the way through the southern oceans. We can look at how storm systems start in the Pacific and impact the West Coast, such as what we've seen just recently with major storms that have caused landslides and other impacts in California. And then we can also start to see different types of convection and daily changes in the Amazon rainforest. So if we go to the next slide, one of the things we can do then is we can start to say, well, okay, if it's raining, well, what happens with the soil? And so, this is just an example of one product of soil moisture. And you can see as the rain, which is shown in green and yellow and red, as that's changing, you can start to see the soil getting wetter, right? So the blue areas show things getting wet. And this seems pretty straightforward. But what's really interesting is we can do this globally with satellites like the Soil Moisture Active Passive Mission and with GPM and with other data that not only tell us about our land, but tell us about the oceans and how they interact. So if you go to the next slide, one of the things that we can do is, in addition to taking individual measurements of rain or soil moisture, we can start to put these into models. And that's one of the things that Goddard does really, really well, is build global models to look at our Earth system. So I could stare at this visualization for days, but what you're seeing here is different types of aerosols. Carbon that's caused from fires. You see dust coming off the Saharan desert, sea salt in the oceans, and even nitrates coming out of different parts of the industrial centers. And so while this is a model, all these different satellites that you saw at the beginning are being brought in to help us understand how these systems are moving. And this is from 2019. You can start to see the fires in Australia and how far that dust and that carbon transports into the southern oceans, affecting South America. And you can see how the dust in Africa is starting to form what we call the nuclei, the starts of hurricanes that affect us in the United States. So one of the things, if you go to the next slide, that I'm particularly passionate about is modeling of landslides. And so that's what I do for my research area. And so the goal here is to say, where has it been raining? Where is the topography steep slope? Where is there vegetation changes? And we can start to look at landslide hotspots around the world and understand how, changes by season, which is what you're seeing now, may impact the exposure to populations because of landslides. So just to close out, Earth science is an amazing field. It's a wonderful, wonderful place to be. And Goddard is just a really tremendous place to bring in all these different areas. Sorry, just next slide. But the thing that I want you to take away with is you can do anything you want as long as you have a direction, right? So I love this quote by Yogi Berra: if you don't know where you're going, you might end up someplace else. So if you're inspired by any of the presentations you see today, make a plan, take science classes, take math and engineering to figure out how you can get involved and make your plan to really make the world and the galaxy a better place. So with that, I'd like to turn it over to Dr. Pulkkinen to talk about the sun.
Thank you very much, Dalia, and good afternoon or good morning, depending on where you are physically located. Again, I'm Antti Pulkkinen, acting director for Goddard Space Flight Center's Heliophysics Science Division, and I will be talking about heliophysics and space weather. Let's go to the next slide. But first, I will talk a little bit about how I ended up at NASA, and this is actually, pretty typical trajectory originally for national scientists in our organization. So if you click once. I did my high school. I'm originally from Finland, from northern Finland. I did my high school diploma. I got my high school diploma from city of Kajaani. That was already back in 1993. Makes me feel really old here. I went to southern Finland afterwards to do my studies. I got my bachelor's, master's, and eventually my PhD from University of Helsinki in the field of physics, in the field of theoretical physics. Next one. And then I was fortunate enough to secure postdoctoral position, just like Dalia explained in her career at Goddard Space Flight Center, and I entered the postdoctoral work at 2004. Let's click next one. And then through various developments, including meeting my wife here in the US, I always tell that I never got to go back home to Europe, but I was really glad to stay here in the US. And eventually, after doing my postdoc, I went through a couple academic organizations, including the Catholic University of America, where I joined the Department of Physics. And then eventually I got my US passport, which took place 2012, at which point I was a little bit in the crossroads, whether to stay in the academia, maybe go even commercial or go to federal government service. And I decided to enter the NASA Civil Service 2013, and this is my current trajectory. And if you click once more, this trajectory has then eventually led me taking on the Heliophysics Science Division acting director role over the past summer at Goddard Space Flight Center. So I've been kind of transitioning over the past few years more on the management side of things. Okay, but enough about me. Let's talk a little bit about heliophysics. So in heliophysics, we study the nature of the sun and how it influences the very nature of space, and in turn, the atmospheres of the planets and the technology that exists there. Our sun sends out this steady outpouring of particles and energy, which we call the solar wind, and the solar wind also carries with it very complex and dynamic magnetic field. Solar eruptions that we call solar flares, or also coronal mass ejections, are the largest explosions in the solar system, and understanding these explosions is at the core of the heliophysics. And if you click once more. And then there's also the space weather dimension to heliophysics. So the studying the heliophysics system not only helps us understand the fundamental information about how the universe works, but it also helps us protect our technology and astronauts in space. NASA Goddard Space Flight Center seeks knowledge of near-Earth space because space weather can interfere with our communications, satellites, and even interfere with our power grids here on the surface of the Earth. Let's click to the next one. And mapping out the heliophysics system requires a comprehensive observations of the sun's influence in space, Earth, and other planets. And NASA operates a large fleet of heliophysics spacecraft that are placed throughout the heliosphere, and those locations or those spacecraft are shown on this slide. Our missions in heliophysics range from missions such as Parker Solar Probe that flies deep into the solar atmosphere, to the farthest human-made object, which is the Voyager mission, which is sending back observations currently all the way from the interstellar space. And each of these missions is positioned at critical, well-thought-out vantage point to observe and understand the flow of energy and particles that flow throughout our solar system, all to help us untangle the effects that our star, our sun, has on and has the impacts of the sun that has on us. Let's click to the next one. Our Goddard Heliophysics Science Division is the single largest concentration of heliophysicists in the world. We have about 350 people working in our organization. And as you can see from this slide, our work is organized under 5 different laboratories. And our work includes work on theory, modeling, and also instrument development work. We also work very closely with our US federal partners and also with our international collaborators, such as our Australian collaborators. And we feed the latest scientific understanding into space weather applications. And the idea here is that ultimately those applications will help mitigate the fury of the sun. Next slide, please. But our greatest asset, of course, are our people within our Heliophysics Science Division at Goddard. And it's all these people that make all these amazing things possible that we do in the division. Our Heliophysics Science Division is a very diverse group of about, as I said, 350 people. Our personnel range from students, even from high school students, to senior scientists. We have scientists working on solar phenomena, heliospheric phenomena, magnetospheric phenomena, and all the way to looking at the upper atmospheric phenomenon. We have public outreach people, we have education experts, and we have also research analysts, system administrators, and so forth. It's a very diverse group that make our heliophysics science happen at Goddard Space Flight Center. And we hope to see maybe some of you listening to this panel join our heliophysics family at some point. So with that, I will pass it to Mr. Mike Amato.
I'm with you. Hi, everybody. My background is mostly in aerospace and systems engineering, and it's what my undergraduate and graduate degrees are in, also from the University of Maryland. But what I think one of the great things about Goddard is how it's a place where science and engineering meet. I'm going to try to give you a few examples of that in planetary science. Next slide, please. For example, let's start with the moon. The Lunar Reconnaissance Orbiter, or LRO as we call it, is a mission led by Goddard. It was launched in 2009 and has 7 science instruments on the spacecraft. But among the many science results are very detailed visual and laser altimeter maps of the lunar surface, which are not only important for science, but also become critical to safely landing on the moon, part of the NASA Artemis lunar program, but also as part of other countries' efforts. On the left, you'll see LRO's laser altimeter topography maps. The blues and purples are lower parts of the moon, while the reds and whites are higher parts of the moon. A large purple region in the south there is the South Pole Aitken Basin, which is the largest impact basin on the moon and almost 2,600 kilometers across. It's also one of the largest impact basins in the entire solar system. On the right is LRO imagery of the South Pole region, where you can see how many areas are shadowed, and some of those areas are always shadowed and become places that collect ice over time. Next slide, please. Moving on to Mars. Part of the Mars Science Laboratory mission is a complex instrument Goddard scientists and engineers built called SAM. The mission's Curiosity rover landed in Gale Crater. Some of you have seen pictures of it on Mars in 2012. And in Gale Crater, sediment patterns show a lot of water was present over many millions of years, including as a long-standing lake, which I find pretty interesting. And to identify organic material in the Martian soil, the team is drilling into sedimentary rocks known as mudstone, which formed billions of years ago from silt that was at the bottom of this lake. The rock samples were analyzed by SAM, which uses an oven to heat the samples over 480 degrees Celsius, and that releases molecules, allows us to detect those organic molecules and other molecules we're looking for from the powdered rock. Next slide, please. Thank you. In addition, SAM just doesn't only measure samples, it can actually measure the atmosphere. It's detected seasonal changes in methane and oxygen. You can see here the methane signal has been observed for over 3 Martian years, and it peaks in the summer. Next slide, please. So another mission is MAVEN, which is Goddard led. Goddard managed anyway, and it's in orbit around Mars now, which has brought new insight in exactly how the sun stripped Mars of most of its atmosphere. And it's turned a planet that was once possibly habitable into a barren desert world. MAVEN's measurements indicate that the solar wind strips away Mars gas at a rate of about 100 grams every second. The Martian atmosphere is now about 100 times less dense than Earth's. Next slide, please. So let's talk about asteroids and OSIRIS-REX. OSIRIS-REX is a Goddard-managed mission that arrived at the near-Earth asteroid Bennu in December of 2018. At 500 meters in diameter, Bennu is a bit taller than the Empire State Building here in the U.S., and is the smallest object, believe it or not, to ever be orbited by a spacecraft. Samples we take from Bennu will provide information about the early history of the solar system and help scientists develop future missions to mitigate asteroid impacts on Earth. Now, Bennu is officially classified as a potentially dangerous asteroid. There's a small but notable 1 in 2,700 chance that it'll strike the Earth in the last quarter of the 22nd century. That's a long time from now. Next slide. So the spacecraft is about the size of a big van. And these images I think are neat because they show the primary and backup sample sites on Bennu with a standard parking lot superimposed over them. So you can get a little sense of size. The primary site is Nightingale on the left there, and it's located in a crater near Bennu's north pole. Next slide, please. So what you see here are images from October. This is showing the OSIRIS-REX mission's touch-and-go sample collection event. This is with a spacecraft sample head, which is extended from the spacecraft, and it shows how it approaches and touches down on the asteroid surface to collect the sample from the sample site. The sample head touched the surface for about 6 seconds, after which the spacecraft performed a back-away burn after capturing the sample, allowing it to pull it away from the surface. Next slide, please. This shows the OSIRIS-REX spacecraft completing the final step of the sample stowage after we've collected it. It inserts it into the sample, and it's closing the sample return capsule. To seal the capsule, the spacecraft closes that lid at the top there and then secures 2 internal latches. That sample is now safely stored, and it's on its way back to Earth, arriving here about September 2023. Sample return science is kind of like a gift that keeps giving because it allows the world's best instruments to analyze these precious samples from early in our solar system for many, many years. And maybe some of you, I hope, will be analyzing these samples in the future. Next slide, please. Let's talk about Lucy. Lucy mission is managed by Goddard as well and is in development and currently in the last stages of integration and test where we put the spacecraft together. Lucy will be humankind's first visit to the Jupiter's Trojan asteroids, and these are planetesimals, or primitive building blocks that form the planets. Lucy takes advantage of some clever flight dynamics design, which you see on the left there, to get to those asteroids, which are captured in two areas near points where the gravitational influence of Jupiter and the Sun balance. Since the Jupiter Trojans have remained trapped in these orbits, mostly untouched for a long, long time, billions of years, they're like fossils of planet formation, hence the name. And by studying them, the Lucy mission will reveal new things about the development of the solar system. Lucy will launch, I think, in October of this year. Next slide, please. Dragonfly is a mission where Goddard scientists and engineers are playing an important role. It was recently selected, and it's a mission with a flyable drone-like lander to explore Titan's prebiotic chemistry and habitability. Goddard's Melissa Traynor is one of the deputy PIs on the mission, and we're leading the teams that provide the sample drill and the primary instrument to analyze those samples, among some other things. One of the areas we spend a lot of time in at Goddard is how do we make the right measurements to determine if a place is habitable or was habitable, or how we would determine if life is there right now or was in the past. Next slide, please. Finally, let's talk about Venus. Goddard recently led a planetary decadal mission study where we'll look at future missions for a Venus flagship mission. A major part of that was the Venus surface lander shown here. In addition, Da Vinci Plus is a Goddard-led discovery mission, which is in the last stages of the discovery competition. This Da Vinci Plus, if it's selected, is a Venus probe and orbiter mission, which will directly sample the atmosphere and take images all the way down to the surface. These Venus missions, which we work on a lot here at Goddard, need to explore the atmosphere down to the surface to answer questions about the evolution of habitability on Venus and whether it had an ocean a long time ago. The surface conditions of Venus can be up to 470 degrees Celsius and 90 Earth atmospheres. Not a pleasant place. And with that, I'm going to hand it over to Dr. Knicole Colon.
Great, thank you. So good morning, good afternoon, good evening, wherever you're watching from. I am excited to be here today to tell you a little bit about astrophysics at Goddard. Astrophysics actually encompasses a wide range of topics, including the study of extrasolar planets or exoplanets, which are planets that orbit distant stars, the study of stars themselves, the study of all types of galaxies, and the study of cosmology, which is the study of the origins and evolution of the entire universe. What I specifically study and will focus on here in my time today are extrasolar planets. Next slide. So this is an artistic rendition of what extrasolar planets or exoplanets look like, or we think they look like. And as I mentioned, these are planets that are found outside of our solar system around distant stars. We actually now know of over 4,000 exoplanets in our galaxy. So based on these discoveries so far, we can say that every star that you see in the night sky, and also all those that you cannot see because they are too faint or distant, all of these on average have at least one planet. In reality, some stars have no planets around them, but others have multiple planets around them, much like our own solar system. So either way, there are a lot of planets out there that we know of so far, and it's a very exciting time to study exoplanets. Next slide. So before I talk about some specific missions that I use to study exoplanets at Goddard, I wanted to tell you a little bit about my specific path to Goddard. As you can see on this map, I moved around the United States quite a bit in my journey to Goddard, but I've also participated in lots of international meetings and spent a summer doing an internship in Puerto Rico. So you know, astronomy and astrophysics and all of science, really, it's a global effort. And where my journey started to Goddard was, I grew up in New Jersey, where I went to college, undergraduate school at the College of New Jersey, and then I moved to graduate school at the University of Florida. After that, I held 2 different postdoctoral research positions. One took me to Hawaii for a year, and then I went back to the East Coast of the United States to Pennsylvania. I then actually went to work at NASA Ames Research Center, which is 0.5 here on this map, which is out in California. And I worked there on a space mission called Kepler. And that was the first mission to really revolutionize our idea of how many exoplanets there are out there, because it was the first mission to find literally thousands of them in our galaxy. But I ultimately knew that I wanted to work at Goddard because of just how many different exoplanet missions that Goddard plays a part in. Next slide. So you can see here a list of these missions, these different exoplanet missions, with all of the currently active ones or future ones in development being marked by the orange arrows. And Goddard really does play a key role in every single one of them. So it's a really exciting time to be at Goddard to study exoplanets so that we can continue to search for more and also measure their properties. Next slide. The first mission that I wanted to focus on, that I specifically work on at Goddard, is the TESS mission, which actually launched in 2018. And it's currently up in space, scanning nearly the entire sky to search for exoplanets. So these images that you're seeing are real images from TESS, and it shows just how much of the sky it observed, specifically in the first 2 years of its mission. TESS is in particular looking for small planets around the closest stars to us that we say are relatively easy to study. And what I mean by that is that it is relatively easy for us to measure important properties like a planet's size and even study its atmosphere when the planet orbits a nearby, close by star relative to our solar system. Next slide. So how do we actually use TESS data to find planets and measure some of these properties? Well, we use what's called the transit method, which there's a graphic shown here to illustrate that. And this is basically where TESS takes a series of pictures of stars, just like you would use your camera on your phone to take a picture, and it looks for regular dips in the brightness of the starlight. When we see such dips occurring regularly, that indicates that there's likely a planet blocking some of the light from our point of view, as illustrated here. Next slide. So this slide provides an overview of the current discoveries from TESS that were made specifically using that transit method. I note that this slide is only a week old. It was made last Monday, but it goes to show how quickly the field changes, because last Monday, TESS had confirmed 98 planets so far. Now we have, just a week later, 107 planets that TESS has specifically found. So things change quickly in this field. And not to mention that there's an additional 2,000 candidate planets that TESS and people who work on TESS are working on confirming as real planets. And at Goddard, I've been lucky enough to contribute to the discovery of more than 10 different exoplanet systems with TESS. And that's really because my role is to help people who are searching through and analyzing TESS data to find exoplanets, or those people who want to make other discoveries as well, because TESS actually does a lot of other astrophysics that I don't have time to talk about today. Next slide. The other mission I wanted to touch on today is the James Webb Space Telescope, which is anticipated to launch in October of this year. And you can see in this picture, it has this gigantic gold mirror that has also underneath it a tennis court size multi-layer sun shield that will protect it from the sun's heat when it goes up in space. You also might notice that the mirror itself is actually folded in this picture, and that's because the mirror has two wings of the telescope that will unfold to result in a total mirror size of 6.5 meters in diameter. And the reason it's folded in this picture, though, is that it actually has to launch folded up so that it fits inside the rocket that will be launching it into space. Next slide. So what will this giant telescope do once it is in space? Well, Webb will build on missions like TESS, and it will perform exquisitely detailed measurements of exoplanet atmospheres. For instance, when a planet with an atmosphere transits its star, we can look at the starlight that passes through the planet atmosphere and also see what starlight gets blocked or absorbed by molecules that are in the planet atmosphere. So with this technique, we can search for molecules like water in that planet atmosphere. This in turn allows us to study the composition of a planet atmosphere and learn how it formed and evolved over time. So my role on Webb at Goddard is to make sure we have all of the tools we need to study atmospheres of exoplanets with Webb once it launches. Next slide. Okay, so that is just a brief look at the astrophysics that is happening at Goddard. But with missions like TESS and Webb and all the other ones I didn't have time to talk about, their scientists at Goddard and also people around the world can use data from these missions to explore the universe in more detail than ever before. The last thing I'll say is that a lot of this data is publicly open and available for anyone to use. So we encourage people to use this data from these missions and make their own discoveries. And so with that, I will pass it back to Ms. Horton.
Thank you, everyone. And I'm just going to take a look at the chat here and see what we have. So the first question is, can people from outside of the U.S. work at Goddard, or do you need to be a U.S. citizen? So Antti, I do know that you talked about internships. So if you want to just talk a little bit about internships and internships with international partners.
Yeah, absolutely. So foreign nationals can definitely work at Goddard. I believe we may have programs even with the graduate students, but certainly so. A lot of our postdoctoral fellows are from outside the U.S. So certainly there are a lot of opportunities for international folks to participate to the work that is being done at Goddard Space Flight Center.
Great, thank you. Dalia, the next question is for you. Is there a web reference that we can go to look at these climate modeling animations? And if you can just expand a little bit on why you chose to do landslides as your background.
Sure. Well, to see more about climate in particular, you can go to climate.nasa.gov, and that has a lot of great resources. And then the Global Modeling and Assimilation Office, GMAO, has some great visualizations. And so if you go to the Earth Science website, you'll be able to find those. In terms of my interest in landslides, I really wanted to see how I could make a difference and how satellite data could be applied in unique ways. And so the landslide community, when I was starting, was just beginning to get involved with how you can take different types of remotely sensed data and use it together for modeling. And so that's what really inspired me into this area, is to try to push the envelope to understand not just what's happening in our backyards, but around the world with different types of satellite data. So that's why I go to work every day.
Perfect. Brian, the next question is for you. So what sort of fuel is used, and is it sustainable fuel?
Yeah, so a couple of different types of fuel. One is hydrazine. So if you want to Google it and look up, it's a pretty toxic type of fuel, not safe around humans. Some of the bigger rockets use liquid oxygen, liquid hydrogen, like we use to go to the moon. Sometimes we keep those really, really cold, which is one of the challenges in space, is having those be able to be stored for long periods and not boil off. Some of the newer satellites use a fuel called xenon, which is a kind of a electric propulsion type fuel that allows you to go very far but very slow, whereas things like hydrazine allow you to go kind of short distances, use up all your fuel but very fast. So it really depends on where you want to go. So a couple different types of fuel that we use in space to move satellites and rocket ships around.
Very cool. And Mike Amato, what is the connection between sending the probe to Mars and sending astronauts later?
Well, that's a great question. I mean, I think one of the most important things is you can't send a human to a place where you don't understand the environment. There's too much at risk. So there's a dust environment, there's a radiation environment. Plus, it drives how you plan that mission. What science you're going to do when you get there? What are you looking for? Well, if you send robotic missions like the probe and the rovers, you know where water might have been. You know where the most interesting things are. So it helps drive the entire mission design because you don't have unlimited resources. You can only send humans to one or two places. So that's the primary thing.
Great. Knicole, I'm going to pass this one on to you. So what is your favorite part of working at NASA?
That is a great question. I think for me, it's honestly that every day is different. You know, I mentioned in my talk that the number of exoplanets from TESS jumped up, you know, by 9 or so in the last week alone. And so there's constantly new discoveries being made, constantly new missions being developed or just new ideas seeded to develop new missions. So there's so much to do, but so many opportunities to do whatever you're interested in. So I think it's a combination of all those things that, you know, is my favorite part of working at NASA.
Yes, and I will say, as a person with an accounting and economics degree working at NASA, you can basically do anything, get your degree in anything and still work at NASA. That's probably my favorite part. You don't have to be a scientist or an engineer, although you guys are very, very cool to work at NASA. So Dr. Hill, since you're still on the line, I'm going to pass this one on to you since I think you'll really be able to answer this question. What are the high demand areas of research in the space agency at the moment?
So there's so many different areas that we're interested in, but as you know, we're trying to put the first woman on the moon, along with a man. That's been something that I've been dreaming of since I was a kid. I thought I really wanted to be the first woman on the moon, and now I'm probably too old for that. So I'm really looking forward to the first woman being on the moon and being a tiny little part of that. And so that's one of the big initiatives. And then, of course, once we get to the moon, the idea is to put a person on Mars and to do sort of the solar system investigation. So there's a big thrust in that direction. Aside from that, there are so many other things, like you've just heard about, predicting climate and understanding climate change and how to protect our planet, understanding space weather, again, how to protect the planet and how to better understand how to keep our spacecraft safe, looking for new looking for evidence of life in the solar system. All of those things are totally cool. So, and we're pushing in directions really using quantum technologies now for better communications as we develop the technologies to go and do those things.
Thank you. And Dr. Pulkkinen, this one is for you. You mentioned space weather and how it affects our planet here on Earth and working with other agencies. What does Goddard do to help protect humans as they go farther out into space from space weather?
That's a great and very timely question. We being the Goddard Space Flight Center, we're working very closely with our other NASA centers, including Johnson Space Center. Johnson Space Center is responsible for providing the space weather information for crews on board these human spaceflight platforms, including International Space Station, and ultimately also on the Artemis platform. So we and our team, actually in our division, we are right now working in very close coordination with Johnson Space Center to provide the latest, greatest heliophysics observations and also the latest, greatest heliophysics modeling capabilities for them to be able to provide that space weather service and space weather information for the crews on board the current and especially the future human spaceflight platforms.
Great. And Dr. Coulomb, this one is for you. Have any Earth-like exoplanets been discovered that may support life?
That's also a great question. So we know of a handful, so a few of Earth-size exoplanets, so things that are similar in size to Earth, and some that might have the right temperature to have liquid water on their surface. And that's one condition that we think is needed for a planet to be habitable. But we don't yet know if these exoplanets that we found that are Earth-size with this right temperature are in fact habitable. We are still working hard to understand their atmospheres and what surface properties they might have. And so it just takes some time, but we're getting there. So, I think we'll learn a lot more in the years to come with future missions as well.
Thank you. And Mr. Roberts, this one is for you. So a lot of students out there, a lot of young people, they, use robots all the time. They play video games here on Earth. But what is different with using a robot in space, and particularly controlling it from Earth when it is in space?
It's a very good question. So if you start off with the design, if a robot you have in your kitchen breaks down, you can very quickly fix it and put a new battery in it or fix a wire that's broken. When you launch into space and it's a couple hundred miles above your head or way out in the universe, if it breaks, there's no way to fix it. So the first difference is we take great care in the way we put things together, the way we make sure they're going to work. We have backup systems in case the primary computer goes down. There's a backup just because of where we are and how expensive these things are to get to space. The other big difference is where they operate, right? Your kitchen is, or outside even isn't that hot or that cold. Some of these places we send robots to in the universe are very, very hot or very, very cold. And so that has an effect on the types of parts we put in the robot. Some batteries, if they get too cold, will stop working. So we have to be careful to keep things the right temperature. So we have systems on board to keep them at that temperature. And finally, I think, as you alluded to in the question, the big delay is when I'm controlling a robot in front of me, I can see it, it's moving, I know where it's going. As soon as I send a command, it moves immediately. Some of these robots, especially out at Mars, when I send a command, it might be a half hour later that it moves. And so it's not like just a joystick where I move the robot and it moves. What's happening in space with the video I showed may happen 4 seconds or 6 seconds from now versus, some of the robots we send way off in the far reaches of the universe, it could be days before they do something. So it depends on where it's going to go, of how much smarts are on board to allow the robot to do its own thing versus having to wait for every command to go to the ground. So a lot of different challenges in space robotics, which makes it fun and interesting, and why we need smart people like out there listening to come join our team.
Thank you. So Dalia, I'm going to pose this question to you. What advice would you give somebody who is thinking about pursuing a career in the space industry?
So the first thing is to get a sound background in math and science. That is the most important thing. They may not be the most exciting classes, but they're definitely foundational for doing really cool things after. That's the first thing. And the second thing is talk to your teachers, talk to your professors if you're in school, in college or university, because they have great insight into the different possibilities of new careers that are out there. And I think that, the careers are growing endlessly every day. And so as long as you have that strong foundation in math and science and engineering, the doors are open to anything you want to do. So please reach out and talk to mentors to help guide you through that process.
Perfect. Thank you. And Mr. Amato, I'm going to pose this question to you. What is the biggest discovery that we have found on Mars?
I think for me, well, I guess everybody's going to answer that question differently. And I think two things for me, at least recently, is it was confirming that we had long-standing water on Mars. To me, that was we knew it was probably true, but confirming it was a big deal, and where it was, because now you can look for those organic materials. And in fact, recently we discovered there were organic materials. You're getting a feeling about where Mars might have been habitable, how habitable it was, what type of life might have existed, if it ever existed there, and where the water was and wasn't. And that, to me, that's the biggest thing about exploration and what the next range of science questions will be for Mars.
Thank you. And the last question that I'm going to pose, and I really don't know which person to give this to because any one of you can answer this question, but how long does it take to develop a satellite mission? So whoever wants to answer.
Maybe I should start that since okay. So I do a lot of the new development, the early phase design, and a mission like Lucy, which is a medium mission, not as big as JW, which you heard about, and not as small as some of the smaller ones. That takes a few years to do the initial design, and if you compete for it or if there's studies for it, and that's a few-year process. That's before you even start doing the final design and build. And usually a design and build for a planetary mission, it's about 5 years after that. So I would say from concept, from paper, from whiteboard to launch, if you're lucky enough to move that fast, it's about a few years of pre-work and 5 years of development before you launch. And sometimes you have to go through the pre-work a few times to even get the mission. So it's about that range. Maybe some of you could add to that, because I know some of you work on JW, and it's a much longer time frame for something like JW.
Dalia?
Yeah, I'll just add that, even before you start talking engineering, you start talking the science questions, and that kind of forms what the engineering, how you build it. And so we're just completing the process of a 2-year study for a mission or set of missions that we hope to launch at the end of the decade. And so it's from start to finish launch for science. It's about how you think of the science questions that really push the envelope. And that's a decade in the making for sure.
Dr. Hill?
So the missions that Michael and Dalia talked about are sort of the big missions, and James Webb Space Telescope for sure is much, much longer than even that. But for the research and development for the new technologies and to do a sort of a demonstration of what might be possible, we do have anything from sort of a sounding rocket, which just goes just up into the atmosphere, just above the atmosphere to make some measurements and back down in 15 minutes. We have balloons that sort of actually, we launched from Antarctica that, in 24 hours may capture some data from way up in the atmosphere. And then we have small satellites that we do that maybe have a turnaround of maybe something like 3 years. They don't do as much. They don't get as much data. They don't answer as many science questions as some of these bigger missions that folks were talking about. But those are the ones where we put the new technologies on and the cutting edge technologies to do a test to see if they do what we expect them to do, to see how they behave in space, and then we can start designing the bigger missions and using those technologies in the future. So as you can see, there's a huge range of size and length of development.
And Brian?
Yeah, and I'll say, and then once the satellites are up there, if you look at the Hubble Space Telescope, primarily due to servicing, it's been up there for over 30 years. So all the work that everyone just said to get there, right, a decade to get there for the science, and then you launch it. Sometimes mission lasts for a few years, a few days. Hubble in that case has last, three decades, which is quite impressive, and it's still going strong.
Thank you guys so much. That is the completion of our panel today and our session. I want to thank all of our panelists for being here today and taking the time out of your day, and to all of the participants who tuned in to the event. You guys had really great questions, and we really appreciate you taking the time to listen to us and supporting NASA as you guys always do. So thank you guys, and have a great rest of your day, whatever that might be.